here I am for homework 4 part D. So to get started, I'm just gonna um, generate some synthetic data. Um, I accidentally turned on Gemini. I don't want it. I don't know how to turn it off. But now it keeps predicting what I'm gonna write, and I don't like it because sometimes it's right. And it's not even like some of this I like typed before, but some of it I haven't, and it still knows what I'm gonna do, and I really don't like that. But anyway, so now starting off with a little rant about AI. Um, yeah, so now we're gonna do a simulation of this. So simulating a time response. So we need our time function. So we'll do a lambda function of t. That's just going to output 1.2. We have n equals 50, dt equals 2.5. And then if we go ahead and enter that, we have our time response, or sorry, our time steps and our height response. So we can go ahead and split that into time in y. And then for our Gaussian distribution here, we'll just do p dot random dot normal of y and 0.05. And now I'm going to go ahead and make a subplot to show what that looks like. Pig dot add scatter of x equals t, y equals y, theta, mode equals markers. I find if I type fast enough, it doesn't have time to generate AI. But so that's my goal. Um, yeah, so we have this curve here. This is our process, and then you see there's just a little bit of noise there. Um, yeah. So now moving on to the next part, we're going to fit an FOPTD model. To define FOPTD, it's going to have time. That's going to have it. It popped up for me. It's going to have Ka, tau, and theta. Um, yeah. So theta is um, our this part doesn't go right away. Um, what is it called? It it's our time shift, our shift. So like if you wait 2 seconds before you start the process, start the change, that would be our theta. And then of course tau, Ka is our K value. That's our controller, or sorry, our gain times A, which is our step change. And then we are going to use this here. So 1 over s tau s plus 1, that's the Laplace form of a step change. Yeah, so we'll return Ka times 1 minus np dot exp of negative of t minus theta, right? So time minus our time shift over tau. And then we want to only return this when time is greater than theta. So np dot where t is greater than theta. All right. And then we can go ahead and do a model. The y model equals FOPTD. We'll do, um, and so we'll actually have to look at kind of what this looks like. So our final value up here is looking around 1.8. And then down here, we start moving maybe 15. And then our tau, our time constant there, is going to be about 30. I mean, that's a very guess answer. but you're looking at like a third of the way up is 30. So you put in 30. So we have time 1.2, 30, and 15. I believe for our Ka, tau, and theta. Yeah. Great. Ooh. Oh. If this is false, I want it to return a 0. Right. And now what I want to do is do a sum squared error. So define SSE given some vector, and that's going to be our Ka, our tau, and our theta. It has all of that code. I've never typed this before. I don't see it. I don't like that it does that. It's like it's right. Oh man. So we have, and it also just gets in the way, makes me like, but I have no idea how to turn it off. I tried. So we have our FOPT of TD of T, Ka, tau, and theta. And then, yeah, we just want to minimize this. So do we have, yeah, we have minimize SSE, and that is going to be with these three values here. So we see we get three values. One of them is negative, and they are all very large. So something went wrong here, to put it lightly. Y model. That doesn't help. Huh. Well, yeah, so about it being squared, I never actually squared it. I will also, it does need to be Y data. Oh, I also, Ka is our final, which is 1.8, not 1.2. I think it should be fine. It could be close enough, but yeah, it's very slightly different numbers there. Yeah, you see, it says 1.8, 1.9, 2.8, and 2.1, or sorry, 28 and 21 are some good values there. So then we'll just retype that as like y min error equals that, and then we'll be able to plot that out. Y min error, and also mode equals lines. Oh, we want only the x from that, right? So if I go ahead and enter there, if I delete that and then enter, there's all this stuff. If we just do .x, we just get that array. So .x, and then we are able to graph it, and it looks atrocious. What happened here? Right, of course. We then need to, so this will be a new vector. I did this wrong. And then we'll need y min error equals our FOPTD of time and that vector. Does that work? No. So Ka, tau, and theta. Ka, tau, and theta. I was hoping I didn't have to write those out separately, but I think I do. So now we have our min squared error finally. um, yeah, and so you can see this approximates the data pretty well. If we were to do just y, how would it look? Oh, I mean, of course, we're not doing the same thing as a step change, or as this, you know, first order plus time delay model shows. Right? There's no time delay, it's just a step change. But this is a pretty good approximation. You know, it does get pretty close. So, yeah, it looks great. So now, instead of that, or instead of this sum squared error, what we are going to do is actually dive more into this FOPTD model. Right, and so we'll be using the PI controller parameters that were calculated back in 1997 for a closed loop response of the system. Right, so just looking at this, we have PA equals 0.586, PB equals negative 0.916, IA equals 1.03, and IB equals negative 0.165. Right, and then here we have y equals, so A times theta over tau to the B, we'll have for our P, right? So that's our PA. That's proportional. So PA times theta over tau to the PB. And then our y equals K times KC, we can actually say KC equals y over K. Now, we don't have K, but we do have is KA, which is K times our step change. Our step change, of course, is 1.2 that we just did in the very beginning. So K equals KA over 1.2. And then we have tau over tau I equals A plus B times theta over tau. Oh, sorry. IA plus IB, right? Because this part is for the integral mode. And of course we can just multiply by, or sorry, we'll do tau over all of this, and that will give us tau I. That's just rearranging, doing a little bit of algebra there. All right, so now we should be good to roll forward with this. Yeah, so we'll go ahead and make our closed loop. We have our GC equals KC times 1 plus 1 over S times tau I. And then our closed loop is going to equal GC times GP over 1 plus GC times GP. Both of these were calculated in, I think, part A. So I won't go through that again, but it is in part A. So now I can go ahead and run our simulation. We have a simulation of G closed loop, and we want a lambda function. This is going to be our time step. I guess I'll just do 1.2 again, and then we'll just run it for a while, and we'll do dt equals 0.5, just so that we have some distance covered. Now we need our t and our y. We can actually call this y servo to distinguish it. And I'll call this T2. to distinguish it, because we do have the other time frame. Yeah, and then we can just, well, not add a scatter yet. We need to make a different figure. So fig2 equals make subplots, and then fig2 dot, it knows exactly what I want. I haven't even typed this, like, anyways. Our x is of course our time, and y is our servo, and we'll want mode equals lines, because this is a simulation and not data points. So here we see our graph shoots up, wiggles a little, and then it gets to 1.2. So yeah, we just see that this first order plus time delay model with, just these values they calculated is actually effective. And so yeah, that's pretty cool. And I believe that is the end. Yes. So this will be the end of homework 4. And yeah, I will see you in homework 5. Thank you.